for our last set of notes for our summer work, I want to talk about a typical type of example, a typical type of lab that we would do in gravimetric analysis. When we deal with gravimetric analysis, the most common thing we do is to find a purity of a sample. How pure is that sample? And percent purity is found simply by taking the mass of the target substance, whatever that substance might be, and dividing it by the mass of the impure sample. Now once you find those masses and divide, of course, this is a percent, so we're going to multiply by 100 to get that into percent form. So one of the things I always ask my students to do is to try to find the impure sample mass first and get that down as part of that particular part of the problem, the last part of the problem, and get that out of the range of vision so that we don't try to use that for something that we don't need to use it for. For instance, let's look at this example. It says an impure sample of solid sodium carbonate is allowed to react with 0.1755 molar HCl. And it says a 0.2337 gram sample of sodium carbonate requires 15.55 milliliters of the acid solution to react completely. What is the purity of the sodium carbonate? So the first thing we want to do is to look at this and decide what our impure sample mass is. Now, they don't just usually come out and say this is the impure sample. They'll just say we've got a sample of an ore, or we've got a sample of this substance, here's what it weighs. And hopefully you picked out that this is the mass of the sample. So what I really always ask my students to do is to go ahead and go down towards the bottom of the problem, the work area, and go ahead and put the percent purity equation. Percent purity, again, is going to be the mass of the substance, which is virtually always what we're trying to find, divided by the impure sample mass. And the impure sample mass we just said was 0.2337 grams. So we've already got that part filled in. We're going to be multiplying that by 100 in a minute. So what we want to find now is how much sodium carbonate is actually in that sample, and that's what we need the rest of the information for. And we're going to attack it the same way we do any stoichiometry problem. We're going to label the equation. So what pieces of information does it give us? It gives us that we have 0.1755 molar HCl. That's what we're reacting with it. So 0.1755, remember from the last time, moles per liter for how we label molarity in a problem. And what else does it give us? It tells us that it requires 15.55 milliliters of that solution to react. So remember, liters, 0.01555 liters of the HCl. And again, we're trying to find the mass of the substance, the target substance, which is sodium carbonate. So X grams is what we're trying to find. So starting this problem out, remember our rules. We never start with a value for the unknown substance. Well, there's not one, so that's not going to be an issue. But for our known substance, we want to start with the simplest unit. And the simplest unit, as it most often is liters right here. So we're going to start with that value, 0.01555 liters of HCl. And using the molarity as a conversion factor, we've got 0.1755 moles of the HCl per liter, understood 1 liter. And now that we've got it to moles, that's our goal, is to get it to moles as soon as possible. Once we get it to moles, we're going to use our mole ratio to change substances. And looking back up at the equation, we can see that there's 2 moles of HCl for every 1 mole of sodium carbonate. So 2 moles HCl for every 1 mole of sodium carbonate. And now that we've gotten it to moles of sodium carbonate, we need it to be in grams so we can put it into the percent purity problem. So for every 1 mole of sodium carbonate, if we look up the molar mass of sodium carbonate, 2 sodiums, 1 carbon, and 3 oxygens, we get 105.99 grams. So that gives us a mass value of 0.1446 grams, which is what we need for our percent purity problem. So moving it back down here, that 0.1446 grams will go here. We've already established that the impure sample weighed 0.2337 grams. Divide that and multiply by 100, and we end up with a 61.88% purity for this substance. Okay, so another way that a gravimetric problem might be stated. It says when a sample of impure potassium chloride, 0.4500 grams, was dissolved in water and treated with an excess of silver nitrate, 0.8402 grams of silver chloride was precipitated. Calculate the percent KCl in the original sample. So once again, we need our balanced chemical equation. So let's do that. We've got KCl reacting with an excess of silver nitrate, AgNO3. And when we react that, we get AgCl, which it said was our precipitate, and KNO3 as the other substance that stays dissolved in water. Now remember, I told you once you get that, the very first thing you want to do then is to pick out your impure sample mass. And it was pretty clear on this one, very nicely told us the impure sample mass and gave us that 0.450 grams of our impure sample. So let's go down here and start our problem for the purity. The percent purity is going to be the mass of the substance, in this case AgCl, divided by the impure sample mass, which is 0.4500 grams times 100. So now all we need to do is figure out how much silver chloride was actually, I'm sorry, I said that wrong. It's not silver chloride. We want to know how much KCl was in that original sample. The silver chloride is going to be the substance that's going to be precipitated out. Using that information, we're going to be able to figure out how much KCl was in that sample in the first place. So let's see if I can write this a little bit better. KCl, there we go. A little bit better, not great still, but it'll do. So let's label everything. It says we started out with that potassium chloride, and when we got done, we had 0.8402 grams of silver chloride precipitated. And we want to know the percent of KCl in the original sample. So what we need to know is X grams of KCl. So there's our problem. This one's pretty straightforward. There's no molarity involved. We simply know grams of AgCl precipitated. We got that all dried and weighed, and now we want to figure out how much KCl must have been in the original sample. So 0.8402 grams of AgCl is our starting point. If we look up the molar mass of silver nitrate, we end up with 143.32 grams. Not silver nitrate, excuse me, silver chloride, 143.32 grams. I was looking at silver nitrate and I was realizing pretty quickly it was not going to be nearly a big enough number if that's what I was looking for. Fortunately, it's for silver chloride. So 1 mole of silver chloride on top. Grams of silver chloride are going to cancel. Now we're ready for our switch the substances conversion factor. Again, this one's going to be easy. It's a 1-to-1 reaction. So 1 mole of silver chloride on bottom to 1 mole of KCl on top. And finally, the grams of KCl that must have been there originally, we can find now by using the molar mass of KCl, which is 74.55 grams per mole. And when we divide this out, we end up with an original KCl mass of 0.4370 grams. So that's our value that's going to go into the problem for our mass on top, 0.4370 grams of KCl over our 0.4500 grams of our impure sample times 100, and I end up with a 97.12% pure sample.